So let me get started. So I'm Anandhi from HP Networking. So DIDM, Device Identification. I think I'm good. By mistake, I pressed off. Yeah. Um, so I would like to go over the scope of the project, what is the current problem, and what is the motivation behind this project, and then some design level architecture, and then what have we achieved in lithium so far, and what are our goals for going forward in beryllium. So I'll just go over these topics in this presentation. So just to start with, right now in ODL, if an application wants to, or if an application needs to send a flow mod or any device-specific configuration, so the application needs to know how to adjust the flow mod or validate the flow mod, create flows specific to that particular device, and then send it. Say, for example, if you take VLAN configuration as well. So different devices may have different set of instructions to configure VLAN. So if you take HP 3800, the VLAN configuration is different from HP 2920. So in order to achieve device-specific functionalities, the application needs to have the knowledge of the configuration or flow mods that has to be sent to the device. So this is the current problem that we have seen in ODL. So we have come up with the solution, like what can we do to solve this problem. So the motivation is to come up with a common solution or common platform or consistent way of achieving device-specific functionality that can be extensible as well. So that's the main motivation of this project. So for example, if we come up with a device driver that can be extended on the fly. So the controller doesn't need to have drivers already installed, or it doesn't need to have the drivers pre-configured so that the device can achieve, so that the application can achieve device-specific functionalities. So the device driver plugins can be added on the fly, like a hot plugin drivers. That's one of the motivations of this project. So the scope of this project is to mainly first identification of the device. So without identifying the device, we can't achieve any device-specific functionalities. So that's the number one priority. And then, okay, upon identification of the device, what is next? We have to come up with the device drivers. The device drivers can do device-specific functionalities. As I said, it can be a flow mod driver, or it can be any other configuration on the device. And then synchronization. Synchronization is something but sending data to the device, or pulling data from the device, which we need going forward to construct, to create and then adjust flows. And then define data models for common features. Defining data models or defining RPCs, these are the two ways of sending information to the device. So we need data model, for example, if it is a VLAN configuration, we need to create data models so that can write instructions to the data stored in MD-SAL mechanism. And then one another component will be waiting for the notification. Once the component gets notified, it can invoke the appropriate driver and then it can send the information to the device. That's one way of achieving what we want through this device drivers. The other one is creating services, and then through services define interfaces, and then the applications can use those interfaces and then achieve device-specific functionalities. So these are the two different types of achieving device-specific functionalities in ODL right now. So the scope is to define data model for the configuration objects, and then define RPCs for flow mod drivers. So in addition to these device drivers, we have also come up with manual discovery, which Gunjan will go over later in detail. This manual discovery is to discover non-open flow devices by just giving the IP address, and then the discovery component will go ahead and identify the device. So we have taken some design considerations to implement these features. One is the, as I mentioned in the previous slide, one is the invoking drivers. There are two ways to achieve that. And any device-specific functionality, we have, as I said, it can be done through device drivers. So if you have pluggable device drivers, those device drivers can take care of device-specific functionality. So the applications do not need to have the knowledge of what do they need to do to apply a flow mod or to apply any configuration to the device. So the main intention is to remove this knowledge from the application. So the application can just send the nodes or set of instructions to the data store. I just want to configure this VLAN configuration on HP 3800, for example. That's it. The component, the FRM component or the configuration manager component, which is listening for this event, will get notified. Once it gets notified, it will invoke the appropriate driver, which will take care of adjusting the flows or sending the VLAN, executing the appropriate VLAN instructions on the device. So these two are the two ways of invoking drivers. One is through RPC mechanism. The other one is through defining a data model so that the other component, model-driven approach basically. So in MD-SAL, the model-driven approach is used widely. So application writes information to the data store in the device table. The listening components like FRM and other components, they get notified. These components will invoke appropriate driver, take care of device-specific functionalities. That is the model-driven approach. Next one is identification. The design consideration here is, once again, identification is done once after the device information is stored in the data store. The identification component, it gets the OpenFlow data or the SNMP data. I'll explain you in detail in the next slides. But just the gist of it here is that for identification component as well, we need to use MD-SAL model-driven approach. Synchronization and driver registration, once again, all the three components, they either use MD-SAL mechanism or we have to use RPC mechanism. So DIDM has very few dependencies. So one is the credential manager, the other one is SNMP plugin. So in order to identify the device, the identification component will use the OpenFlow specifications, which was entered, which was created when the node is created for a new device. Or if the device cannot be identified with the OpenFlow information, the identification component will check with the SNMP plugin to find that since it has the sysobject ID, using the sysobject ID, it will try to identify the device. For that, it has to interact with the SNMP plugin module. So to communicate with the SNMP plugin module, it has to, we need the credentials, so we have to integrate with AAA for credentials.
So just a question, the SNMP, is it the old SNMP for STM, which is ESAL based on
Sorry, it's a separate project, it's a separate component.
Okay.
We are creating it, yes. We have invested in that SNMP as well. Yeah, SNMP, yes. Yeah, we have a sample driver. We have a driver for HP 3800, and SNMP plugin is already released as a new project that supports this basic get set operations that can be done on HP 3800.
So we have a MD-SAL version of SNMP, right?
Yes. So here I just wanted to highlight some of the enhancement requests or backlog items that we have requested for this project to the MD-SAL team. One is that ability to control how much processing is given to a plugin. So this is the CPU processing. So this is mainly needed for manual discovery, with that Gunjan will be covering soon in detail. So for manual discovery, we may have multiple threads running to discover the devices. So we have a requirement to identify the CPU processing being used by each thread so that the priorities can be assigned. So that Gunjan will cover later. This is one of the requirements from our side. The other one is finer filter of data change notifications. So right now what happens is that we have a data store in MD-SAL. Whenever an application writes data into the data store or the identification components after augmentation, if it changes the data in the data store, the drivers are getting notified. So we may have n number of drivers, one driver for 2920, one driver for HP 3800, one driver for HP 5400. So there may be n number of drivers, right? So when the data change notification happens, so the notification is sent to all the drivers. So the drivers have to choose and then find out, is it for me? Or if it is not for me, let me just ignore. So this notification is a performance hit, I would say. So in order to avoid that, we have placed a requirement that, just give us the notification that we are interested in. So HP 3800 is interested in only the notification that is specific to HP 3800. So the augmentation, the notification basically, it can be based on augmentation type or, state of the device. So that can be the filter criteria we can specify. So if the augmentation type is basically, after augmentation, if the device type is 3800, then HP 3800 driver will listen to it and take appropriate action. So right now, all the drivers are listening to all the notification change events. So we have placed a requirement to define filters for the notification. Yeah, augmentation is done by us as well. Okay, the identification component does augmentation. Once the augmentation happens, augmentation is basically nothing but adding more device details to the existing device information in the MD-SAL data store. So we are once again using MD-SAL mechanism to identify, to send the notification to whoever is listening, and then for registration and everything. So yeah, so once the augmentation is done in the MD-SAL data store, the device drivers that are waiting for listening to it, they'll get notified and they do appropriate action. So this is a simple picture. I have two pictures to describe the architectural overflow. So this picture, I just want to highlight the main identification component here. Okay, so the first one is, this is the driver plugin. When the driver plugin gets installed, the driver plugin writes the device identification information. Say, if it is a HP 3800, then it is going to write the OpenFlow information specification for HP 3800, and then this is object ID, some basic informations into a data store. And then when a node gets connected to the controller, an inventory node gets created. We will see that in the next picture. So inventory node gets created. When the inventory node gets created, so identification manager, which is listening for create node, will get notified. So as soon as this gets notified, this will try to match the OpenFlow information which is already there in a different data store, which is added by this plugin, with the OpenFlow information that is created and added by the OpenFlow plugin module. If it matches, then the device gets identified. If the OpenFlow doesn't match, it will compare it with all the device drivers. If it doesn't match, then it has to go through SNMP plugin, SNMP way of identifying the device. So the main step here is that when the device driver gets installed, this is a pluggable driver which I'm explaining right now. This is a pluggable driver. The device DIDM's main functionality is to come up with drivers to attain device-specific functionalities. So this is a device driver, pluggable driver. When it gets installed, it will write the device-specific information. This is going to be used by the identification manager later. So this is a bigger picture, that goes from all the way end to end, what happens when the device gets connected to the controller, all the way up to the routed RPC registration. So let me explain this once again. So the first one is, when a node gets connected to the controller, the OpenFlow plugin discovery component creates a new node in the MD-SAL data store. It's an inventory node. So as I said, when the inventory node gets created, the identification component manager gets notified. So then the identification manager tries to compare the OpenFlow information which is already returned by this drivers. We have a number of drivers here, and compares it with the OpenFlow information which is already put together by this OpenFlow plugin module, tries to find out, identify the device through OpenFlow mechanism. So if it cannot identify the device, then it just uses SNMP plugin to identify the device. If the device can be identified through either SNMP way or through OpenFlow way, then it's going to mark the device as unknown. So and then that's so once okay, let's see. So that's the step 3. So step 4. Once the device gets identified through either SNMP or OpenFlow, then this one, the identification manager augments the device, basically augmenting the device with device type. Okay, I have identified the device. So this is a HP 3800. In this example, it's going to add that information to this node, inventory node. So once this augmentation happens, then the drivers that are registered to get notified for this augmentation. So there are 2 types of augmentation right now we have done. One is device type augmentation. The other one is device state augmentation. Device type augmentation is just adding the device type on top of the existing device details that are there in the inventory node. The device state is, that is another requirement by the discovery team. That when it can be offline or online, or they're currently in the synchronizing state, which is used for manual discovery. So there are 2 types of augmentations that are right now covered. So once it happens, then this driver plugin gets notified. So if it is the HP 3800 in this example, then this device driver apply augmentation with data collected. So this is, once again, there are 3 components you can see here in this plugin. One is the identification part. That is, when the plugin gets installed, it is going to write the device identification information into the data store that we have seen in the previous slide. So that's the first step. And then synchronization. Once the augmentation happens, when this driver plugin gets notified, it is going to synchronize the data from the device. So synchronization means it can either collect the data from the device or it can send data to the device. So for example, in this case, in the HP 3800, we are not doing any synchronization, but this synchronization is widely used by manual discovery. So that's the synchronization. So what happens is that once synchronization happens, it will add that data to the inventory node, which is already created. And then the next is a driver part. The driver part, it can be a flow mod driver or VLAN configuration driver, whatever the device-specific driver that we write. That driver gets notified that augmentation has happened, and then it will go and register the routed RPCs. Basically, the driver can come up with some APIs for the applications to use, or the driver can register itself for data change notifications. So in this case, there are 2. It is an OR right here. So what does it mean is that there are 2 ways the device-specific functionalities can happen, right? One is through routed RPCs, or API. It's nothing but a set of APIs that the application can use. It will register those APIs to associate it with the inventory node. So for this one, with the VLAN driver, and then list of RPCs, APIs. So the applications can use that. The other way is that it is going to data change notifications. So it is going to register itself for data change notification, so that when the application sends or writes a table, data in the table, for example, I want to do VLAN configuration, I want to send this flow mod to a device. So then this will get notified. So who will invoke appropriate driver and execute it? So that is nothing but, I haven't specified here, but there is another component, FRM component, which is done by OpenFlow plugin projects. That FRM component is Flow Resource Manager component. Flow Resource Manager component is listening for data change notifications. When it happens, then it invokes the appropriate driver to push the flow mod to the device. So similarly for VLAN configuration, we need to, for the next, that's one of our goals. We have to come up with a new component here. If we go through model-driven approach, if we go through routed RPC approach, routed RPCs will be available, and then the application can use it. If we go through this, model-driven approach, then a component manager has to come up. It has to be developed. That component manager will be listening for data change notifications. Then that will invoke the appropriate driver for VLAN configurations. So so from here I'll hand over to Gunjan to go over manual discovery process.
Good afternoon. My name is Gunjan. I work with Ciena. First of all, thanks for staying after 5 o'clock. I know it's hard. It's last day of the presentations, and thanks for staying after 5. I'll just go over a bit of history about the project. Initially, this started with, we had a project called Discovery. It was part of, was supposed to be part of Helium. Then HP came up with the driver framework, and there was a huge overlap. So we decided to merge the project, and that's how DIDM was born. So Anandhi talked about the driver framework, how we can load drivers, and sorry, there are two main parts to the project. One is the driver, and the second one is discovery, manual discovery, which was covered by the discovery project previously. So manual discovery is for non-open flow devices. If you have non-open flow devices in your network, you want to discover them. It goes beyond discovery. It's also lifecycle management. So it manages these states of your device throughout the life cycle of the device. So it goes through device identification. Besides what Anandhi explained, there's a manual identification process, which is a bit different from open flow device identification that she explained. And there's a future work integration with credential manager from AAA team, which is going to integrate a credential manager. So you have credentials to connect to the device. Then device synchronization, get the inventory of the device, all the ports and capabilities and stuff. It also manages communication up and down. If your device drops off the network, it loses connection from the to the controller. It also manages that. And there is a concept of managed and unmanaged state, which we'll talk about later. So this is how manual discovery gets invoked. I'll talk about the exact process when it's invoked, but this is the request state. It goes from identification, if it fails, identification failed state, identified, and here between this, once we have the credential manager working, it will use the credential manager to identify the device. But for now, you have to enter the credentials when you invoke the discovery of the device. Then it goes to synchronization, and synchronization could fail. I'll talk about synchronization in more detail in later slides. Once it's synchronized, it goes to discovered state, and discovered that means it's managed and it's discovered in the controller. Now, for whatever reason, if the device communication goes down, it goes to comms down state. If it comes up, comms up state. And then whenever it comes up there, it goes through synchronization again, in case if it lost some port or some connection. And while all this is happening, we are keeping track of the state that's associated with the device. Now, this is device state, as I talked about. So when it goes through the discovery, it reaches final state of discover. That's one of the device states which is associated with the device, not the request. So it's right here in the center. Communication down, up, synchronization. You can also delete the device from the controller. You can also move it from managed to unmanaged. So it's in the controller, but you're not using it for path calculation or anything. And even if it's in unmanaged state, it goes through. It can go through communication up down. It keeps track of that. And that's all in state augmentation. Okay. This is the manual discovery flow. So you you invoke the manual discovery from client, could be REST call or anything, or from the user interface. Goes to config tree, then data change. So when you invoke the manual discovery, you specify the IP address. At the same time, right now you have to provide credentials, login credentials to the device. Then data chain notification gets to identification manager. And it will try to connect through SNMP. In this case, it's going through SNMP first. Remember, this is not OpenFlow discovery. This is manual discovery. So device doesn't talk to the controller first. We have to invoke the discovery. SNMP, then SNMP plugin talks to the device. You get OK back here. And then you're determining the type and adding it as an augmentation. Now, after this, there can be two possibilities. The one in green is either you identify the device through SNMP. So you identify the device and put the augmentation type in the inventory node. And the second possibility is you can't identify the device. So you mark it as unidentified device. You publish that. Now, what happens in the second scenario is in the next slide. Okay, so once from here, when you publish that the device is not identified through SNMP, you go and so at the same simultaneously, if you have multiple device drivers registered, in this example, I'm showing Ciena 6500 and 5430, two plugins, drivers installed. So in your network, you have 4 devices. You'll have 4 of these. As soon as this is received, it talks to the network element plugin. Simultaneously, they will try to connect to the protocol plugin, TL1 or Corba, or any plugin you're using. I should have shown this as 2 separate things, but you get the idea. Yeah. It's Java code. It's an actual module. We have broken it down into 2: network element plugin and protocol plugin. Protocol plugin is generic, TL1 Corba, whichever protocol your device is speaking. So multiple device plugins can use the same protocol plugin, and the device plugin is it knows how to talk to your device. It will make the connection to the device, get the inventory, because this is manual discovery. So if you have a Ciena device which doesn't talk OpenFlow, or any other device which doesn't use OpenFlow, you need something that understands the language on how to connect to the device, how to get the inventory ports, etc. So yeah, it is Java code, and it's a driver that's registered. Okay. Yeah. We use this internally at Ciena, but this is not. It's not open sourced. Okay, so in this example, we are assuming that the device type is 6500. So both plugins will try to connect to the device at the same time. Only one of them will get OK, because if it's not the right device, you will get fail from 5400 device. Fail gets propagated here, and it dies here. 6500 one gets OK, gets back to any plugin. And then you put type. You identify that it's this device type, and you discovered it through this device plugin. And it gets to the operational data store. Now, I'll talk more about synchronization process. This is a device synchronization process. This can be invoked manually, or it's also part of the here. When communication comes up, you go through synchronization. And another one is when you're discovering, you have to go through synchronization. So I'm talking about these two steps right now. Okay, so this is manual synchronization. You can invoke synchronization manually, or it's in the process of discovering or after communication comes up. In this example, I'm just showing you're manually invoking synchronization. So you manually put syncing state to the configuration data store. Another thing is you can also use this if you think you have a device and you don't have the correct inventory information and you want to update the information. For example, you added a new line card and it's not getting reflected in the inventory. You can manually invoke synchronization like this. Then data change notification gets to any plugin here. And then any plugin says, I'm syncing, I'm going to the synchronization state. Remember, for every device, we are keeping track of the current state of the device. It's synchronizing, it's identified, identification failed, it's discovered, unmanaged, deleted. We're keeping track of all the states. So that's what it's doing. State is synchronizing right now. Then you go to protocol plugin and say get data. Goes to device, gets the data, port information, firmware, software, etc. Gets the data, and then you merge it to the inventory node. Instead of updating, you just instead of overriding, you're merging it with the existing data you have in the inventory with data, and then you finally change the state to synchronized, so you know that it's done synchronizing. Yeah. So that was manual discovery. There's a lot more to that. If you're looking for manual discovery code, although the project is deprecated, we are in process of merging it with DIDM project. But you can find the code on the Git page. For the DIDM project. This is what we have delivered in Lithium, and this is what we're planning to deliver in the next release, Beryllium. One of the major things is flow mode drivers, which we're going to work on for the Beryllium release. And then features like VLAN feature, VLAN driver, flow mode drivers, possibly VXLAN driver. Maybe that's after Beryllium release. In VLAN driver, you add VLAN, delete VLAN, add port, remove port from a specific VLAN. And then another thing is to merge manual discovery code with DIDM code in the same project. Just add a feature to install all the DIDM features at the same time, and a tutorial. We also have a Mininet driver as an example, if you want to look at the code and how to write your own driver. This is our wiki page. And you can also look at our Trello board here. And documentation, you can find the documentation here. And developer guide, still have to add some more things to the documentation. That's it. Thank you. Yeah, any questions?
So you guys talking about supporting flow mods for the Korean time frame, right? So
Yeah.
what about meters, regular meters? Because depending on the device, like the number of meter mods that you can create, like the number of meters that you can have.
Yeah, so we'll be considering meters, adjusting flow mods, validating flow mods for at least one device. So in addition to that, we'll be writing a configuration manager that can take care of pushing the VLAN configuration to the device, so which is not available right now. We're talking about manual discovery.
This one? This is for manual discovery. So you're synchronizing all the information about the device, number of ports, port status, firmware, software version, link status, and stuff. You're synchronizing the device information.
So let me make it clear. So I think for the flow mod drivers and other VLAN configuration drivers, we haven't done any synchronization part so far, because if you take flow mod, we have the table features of the device, which is already collected by OpenFlow plugin right now. So we made the request, and as part of the inventory, the OpenFlow plugin is collecting table features for that device. That is already stored in the MD-SAL data store. So we have enough information right now about the device to validate the flow, or construct flows and adjust flows. So if so the synchronization part is not needed right now for HP 3800. So far we have written one driver. So going forward, if it is required, then we will write synchronization in the flow mod driver as well.
And this synchronization is for manual discovery, the devices that don't have OpenFlow support. So synchronization will be part of the plugin. Device-specific plugin knows how to talk to the device and get the device-specific information to the controller.
No, yeah, not yet, yes.
No.
The configuration is not yet done, actually, if I say correctly. The device-specific configuration is one of the motivations of this DIDM project. So far, what we have done is just, how to come up. We have come up with the identification component that can identify the device, and then we have written a sample driver as well as HP 3800 driver, which will, just after identification, then it will just go and register something. That's it. There is no flow mod driver. There is no configuration, which is not yet available. So that's one of the planned features of Beryllium.
All right. Any other questions? All right. All right then. Thank you. Thank you.